build quantum technology, so to speak. And the United Nations have declared 2025 as the year of quantum science and technology. They've recognized 1925 as the year when Heisenberg sent a particularly important paper to one of the journals to look at this notion of uncertainty. And therefore, the UN decided to leverage this, the 100 years since then, to declare the International Year of Quantum Science and Technology, particularly to raise public awareness of the importance of quantum science, the application to all aspects of life. There's been significant investments, both from a public sector perspective as well as from a private sector perspective, huge amounts of government investments. The UK was one of the first countries to have a national program. We started back in 2013. The US has a national program. The EU has the quantum flagship program. China has a quantum mega project, huge amount of funding. India has a national quantum missions program. Significant amount of private investments as well, over 1.1 billion. And one of the largest recent private sector investments from a venture capital firm is into a firm called Quera, which is a firm that is spun out of Harvard and MIT, and received close to 230 million in funding just a few months back. A number of firms have already been listed on the New York Stock Exchange and NASDAQ. Some of the firms are listed here: IonQ, Arcade, Rigetti, D-Wave, Quantum Computing. And the application areas are quite wide-ranging, looking at sensing and imaging, communications, as well as computing. So if you take sensing and imaging, the idea here is some of these quantum particles that are able to leverage quantum mechanical principles are able to sense gravitational forces as well as electromagnetic forces much better than existing classical technologies. Therefore, it can be used to sense things like for biomedical applications, as well as things below ground level, improve timing, i.e. have better clocks, and to help with navigation of aircrafts as well as seafaring equipment, and so on and so forth. From a communications perspective, there are opportunities to use some of these quantum mechanical principles to derive more secure keys in order to encrypt and transfer data, and therefore there's an opportunity to have more secure communication approaches. Finally, from a computing perspective, the principles of quantum mechanics allows quantum computers to compute faster certain types of problems compared to high-performance digital computers, and therefore there's significant opportunities there too. If we then ask ourselves what's driving the need for quantum computing, it's partly driven by the fact that in microprocessor technologies, as we shrink the microprocessor to a smaller and smaller size in order to put more into a transistor, we are getting to a level where it's not possible to shrink it any further because the quantum effects kicks in below the subatomic particle level. And therefore, we need a different technology. And one possible technology is looking at quantum computers. And also, more recently, there's been an exponential increase in computation time, given the growth of data, and therefore there's a need to do more computation at a faster and faster speed, and that requires a different technology to complement digital computers or digital technology. There are potential breakthrough capabilities, particularly in optimization. So the financial industry is looking into this in order to have better valuation of securities, more improved fraud detection. The energy sector is looking at how do you optimize the delivery of energy, especially when there's distributed generation of electricity and energy initiatives, so to speak. So therefore, there's a need to optimize the infrastructure, the energy infrastructure. And thirdly, is another application is in manufacturing operations. There's a need to optimize the operations on a global scale, looking at how do you share resources and facilities across different manufacturing operations, and there's an opportunity to optimize better. The other area where there's potential application is to simulate quantum systems, so to speak, particularly new drug discovery. So it takes a long time to develop new drugs these days. For example, it might take 10 years to develop a new drug, partly because there's a lot of experimentation taking place in wet labs, and it's impossible to simulate the complexity of some of these drug development processes. And there's an opportunity to use quantum computing to better simulate and therefore improve or speed up the process of drug discovery or new materials materials. For example, if we look at clean energy, the development of battery technology requires new materials, and hence quantum computing might be able to help. And in addition, I think there's a significant need for improving the speed of AI and machine learning, and hence the possibility of using quantum computing to enhance the speed of AI and machine learning capabilities is potentially there. And if we go back and say, where did it all start? There was a very famous professor called Richard Feynman. He had won the Nobel Prize in 1965. He was based at Caltech. And in 1981 conference at MIT, he made this observation, so to speak, that nature isn't classical, i.e. the fact that if nature isn't classical, it's actually quantum mechanical. And if you want to make a simulation of nature, you'd better make it quantum mechanical. And by golly, it's a wonderful problem because it doesn't look easy, i.e. what he was saying is, if nature is quantum mechanical in principle, you need a quantum mechanical system in order to be able to simulate nature, and that's not easy to do. And he was effectively talking about simulating molecules and materials. So this is back in 1981. So what's the logic of what Richard Feynman had said? One can think about it in simple terms as, imagine we have 2 balls, the red balls, and 6 boxes, and we need to place this 2 balls into this 6 red boxes. And if we look at the number of combinations, there are 15 different combinations we can place those 2 red balls in those 6 boxes. But let us assume that the problem increases just by 2-fold, i.e. now there's 4 balls and 12 slots. The number of possible combination increases to 495. Now, if we then increase it by another 2.5 times, i.e. there's 10 balls and 30 slots, there are over 30 million combinations. So you can see this exponential increase in possible combinations. And this is not terribly different when we look at an atom and the electrons spinning around the atom. And effectively, if we can think about those electrons as the red balls, and the orbitals of these electrons spinning around the within the atom as the boxes, so to speak. So now if you're thinking about new materials, we are combining this different electrons and combination of atoms, and therefore the possible combinations that can be created is very, very large, and hence it's very difficult or almost impossible in terms of time for a digital computer to simulate, so to speak, this possible combination. So that's why we need a quantum computing or a quantum technology to do that. Now, it appears that not very much happened since Richard Feynman made his remark back in 1981 until about the 1990s, when a gentleman called Peter Shaw managed to show that our encryption system, i.e. majority of the encryption system that we use on our computers and the internet is based on what is called prime number factoring. So that's a very simple way of looking at it is, if you look at number 21, there are only 2 prime factors to get to number 21. You've got to multiply 7 by 3. And what a computer does, effectively, it generates a very, very large prime number and works out the factors for it, and therefore encrypts the data using those prime factors in order to send data across the other side, and the receiving person is able to decrypt it because they know the keys behind the prime number factors. So therefore, the entire encryption system is based on the fact that the digital computers cannot break and cannot find those prime factors fast enough, i.e. within the time frame that the data is useful, and hence we are reliant on algorithm that takes too long to work out in terms of the solutions for a particular mathematical puzzle, so to speak. So Peter Shaw showed that if you had a quantum computer, because it's able to accelerate the process of finding a solution, it's possible to break the encryption that is currently available or used generically across the internet and our computers and our phones and so on and so forth. And that's when this idea of, there's a possibility of harvesting the data today in order to decrypt later came along. And hence there was a much more focused attention in terms of using quantum technologies, particularly for communication and building quantum computers following this particular discovery back in 1994. Now, just quantum mechanical principles are fairly complex to understand. I must say that I'm not necessarily an expert in this area, but just to give you an intuition of how this works, I think there are two principles in quantum mechanics that are very helpful to understand, and that's what's driving what is called the second quantum revolution. That is what's in principle is called superposition and entanglement. So effectively, what we're saying is these quantum objects, which can be an atom, an ion, an electron, or a photon, and so on and so forth. So these are particles or subatomic particles, have got a certain property called superposition. So if you look at a classical bit, which is based, which typical digital technology is based on, they use classical bits where we are switching electricity between 1 and 0, i.e. We can either have it on or off, so to speak. All transistors and semiconductors work on that basis, and we're using the notion of the digital bits in order to be able to do computation. Now, it so happens that in quantum mechanical particles, these particles can be in a superposition, i.e. they can be in a state of 0 and 1 at the same time until you take a measurement. So the way to think about it is if you flip a coin, and the coin can be in the state of head and tail at the same time until you actually kind of catch the coin and have a look at it, it can only be in head of either head or tail, so to speak. So when you take a measurement, it can only be head or tail, but in the process of not being measured, the state is in a superposition, which means it can encrypt more data into the system compared to a classical bit. The second important element is called entanglement, i.e. two particles can be entangled in such a way, i.e. they're related in a non-local sense, where if you entangle them, you take a reading of one of them, and let's say one is in a state of 1, the other one will be in the opposite state, i.e. state 0 or state 2, so to speak, right? So it's completely opposite to the one that you've measured. And hence the idea that you can entangle these particles, and they can be in superposition, and entanglement means that you can actually encrypt much more data than a classical bit, so to speak. And there was a first quantum revolution because in some sense, transistors and lasers tend to use quantum mechanical principles as well. But the difference is today we are able to actively manipulate those properties of quantum systems in order to be able to do computation, measurement, and communication. So just to again give you the intuition of why is it possible to use a quantum computer to speed up computation, a simple way of looking at it is imagine you've got two boxes, and you've got a cat, and the cat can be in one of these two boxes. Now, if you had a digital computer with classical bits, you have to check both boxes, so to speak, i.e. you have to do two sets of check. You have to check box A to see whether the cat is there or not. And then you have to check box B to see whether the cat is there or not. And therefore, you can determine which box the cat is likely to be in, so to speak, or is in. So a digital computer will require two checks of that box in order to be able to work out whether the cat is in box A or box B. But a quantum computer, remember I mentioned earlier that a quantum computer, a particle can be in the superposition state, and it can be entangled. So therefore, in some sense, what we can do is we can put a particle in a superposition state and entangle it, and effectively do a check of both the boxes at the same time. And because they're entangled, if the cat is in any one of those boxes, the state of the system will change. And therefore, we are able to work out whether the cat is in box A or box B in one single attempt, so to speak. So therefore, compared to a digital computer, we are able to reduce the number of steps in doing computation, and the same principle applies to however big the problem space is, and therefore the enablement of parallelism reduces the number of steps, and therefore we can increase the time or reduce the time in which a particular computable problem can come up with solutions. So that's the broad principle, the idea behind a quantum computer, and what a lot of the companies are doing is to engineer the particles in such a way that you can increase the number of qubits, so to speak, i.e. quantum bits, and hence be able to do more and more complex operations. Now, I want to emphasize that it's not likely that a quantum computer will replace a classical digital computer. For certain types of problems, the simpler problems, as we can see, the classical digital computer will still be better than a quantum computer. But as the problem space becomes more complex, it's likely that a quantum computer will be more efficient and then would have, in principle, a quantum advantage. So therefore, it's likely in the future that a classical digital computer will work in tandem or in a complementary manner with a quantum computer in order to solve problems. Now, in order to understand the impact, I like to look at the impact of this technology on economic growth and productivity. It's always helpful to go back in time and have a look at what happened to digital computers. So this is a classic statement made by Robert Solow, who was a professor at MIT back in 1987 when digital computers was being used quite extensively. And he made this remark to say, you can see the computer age everywhere, but in the productivity statistic. It doesn't seem to show in productivity statistics because productivity growth rates was actually slowing down despite the emergence of digital computers. So we got to ask ourselves why? Why did that happen? And to some extent, we need a conceptual theory, I suppose, to understand this. And one way in which we can look at this is what I call a multi-level perspective. So we can look at when a new technology comes along, there are always niche experiments done by new firms. They're coming into the market to try new things. At the meso level, there would be incumbent firms with existing business models that seem to generate a return and therefore will try to, initially anyway, to block the development of any new technology. And at a more macro level, there could be structural changes, i.e. social and economic changes, for example, the climate initiative and so on and so forth, driving some of those sustainability issues. And the combination of the micro, meso, and macro levels will drive technology adoption. So we need to ask ourselves, to what extent do we need to intervene in the market in order for a new technology to be adopted and drive economic growth? Do we need a mission-oriented state intervention, or is the market good enough, or is that a market failure, so to speak? And the second related question is the technology complementary to the existing technology, or is it disruptive? Now, we proposed in one of our papers recently that we think that quantum computers would cause a much larger slowdown in productivity growth compared to digital computers. So this is the data in the US for digital computers. So if we look at the growth rate of output in the US between 61 to 75, and then 76 to 1990, and then between 91 to 2005, there was a dip in the growth rate. This is what Robert Solow was referring to when he said we can see computers everywhere, but not in the productivity statistics. And there was a 0.76% slowdown, which translated to about US $23 billion loss per annum, so to speak, right? So the growth rate was at the 2.04 level right through that period, 76 to 90, the GDP output would be $23 billion larger per annum. So there's a significant loss. Now, we needed a significant amount of business model innovation for the productivity to take off in 91-2005 period. Examples are, for example, in the retail sector, Walmart was investing quite heavily in some of this digital computing technology, but it took them about a decade or so of investment because in order to improve their forecasting and production processes in their supply chain, they needed to digitize not only their own processes, but help digitize the entire supply chain processes so that they can share data in order to manage the inventory levels as well as the production system much better. And that's when productivity really took off. So there was a significant amount of changing core processes and business models from productivity improvements to take place. Manufacturing was very similar. Most of the manufacturing firms initially adopted digital computing technology in order to improve existing processes. Things that they were doing manually was just transferred into a digital architecture, but nothing much changed. Only when they realized that, well, if I got a digital architecture now, it's easier for me to customize the product, and therefore I have variety, my product variety increases. And if that happens, I can use things like computer-aided design, and I need to connect the supply chain in order to balance the production and forecasting much better, and therefore be able to deliver much personalized product and services to customers. And that's when productivity really took off. So there's a lot of changes in the underlying core processes and business models that needed to take place for productivity to take off. Now, if we now look forward and compare what happened in the past with digital computers to potentially what's likely to happen with quantum computers, there are a number of similarities, but there are also significant number of dissimilar aspects, so to speak. So we look when digital computers came on board, they replaced the previous generation technology that was out there, which is electromechanical computing machines. Now, if we look forward at quantum computers are unlikely to replace digital computers. They are likely to be complementary, which means that there will be much significant integration costs between a quantum computer and a digital computer. And initially, the benefits are going to be very marginal. So if you look at the benefit to cost ratio, the initial effect is it might have a significant effect in slowing down productivity because there's a massive cost compared to the previous generation technology, digital computers to electromechanical computing machines, compared to what's going to happen in the future, so to speak. So there's some of these, a lot of these computing technology is not ready yet. They've got a pilot quantum computers out there, but none of it are commercially available. But as they become commercially available, this is likely to happen. Secondly, if we look at, there's a cognitive drag, right? So in the sense that a digital computer is relatively easy to understand because we're effectively switching electricity on and off using transistors and semiconductor microprocessors and so on and so forth. And therefore, the business managers and engineers can keep it under the hood. We don't necessarily need to understand all the nitty-gritty of how it works. And that was very helpful. But when we look at quantum computers, the quantum mechanical principles are quite difficult to understand, and therefore the translation cost between the scientists, the engineers, and the business managers is going to be significant. And we see that quite a lot because the language that they use is quite different, and therefore the cognitive drag is going to also affect the productivity growth. And the third level is that when digital computers came on board, there wasn't a cryptographic threat, so to speak, right? Whereas quantum computers, as I mentioned earlier, can actually break the existing encryption system. And therefore, most firms will invest in order to protect themselves against the threat of a cyber attack or a encryption break before they will use the computer, a quantum computer, for value-added initiatives. And hence, there'll be a significant cost because of this cryptographic threat. And the combination of these things will drive economic productivity growth down before it takes off. So therefore, the question then arises is what is it that we can do in order to at least limit, if not eliminate, that decline in potential productivity growth? And this is where the thinking about core process and innovation and business model innovation comes in. One is, as we've done a fair amount of work around this, talking to some of the potential users as well as suppliers in this marketplace, most of the time the experimentation is being done at an R&D level. If you go to BT or you go to BP or any of the large corporations, the experimentation of some of these quantum computing technologies being done at an R&D level is yet to be escalated up to a very key strategic level, so to speak. So the application areas is fairly marginal, and the suppliers have very little incentive to pull all of the different components part together. So the photonics firms compared to the software developers and so on and so forth. So, and hence, in order to incentivize the market to really take this technology seriously, we need a mission-driven initiative, i.e. to align incentive of the users and suppliers. And this is where the government needs to step in to say, can we show the proof of concept on a problem where none of the industry players would want to solve it individually? They would not have an incentive to do so, but will be collectively interested in solving it, so to speak. So if we look at the improvement of weather forecasting, no individual firm would want to invest in improving weather forecasting, but if a better weather forecasting system is there, everybody would want to use it. Or financial market stability. None of the banks would want to invest in improving the stability of the financial markets, but a stable financial market is useful for the operation of the marketplace itself and therefore the profitability of these banks. So can we actually develop a program where we demonstrate the possibility of using some of these quantum computing technologies as a proof of concept on some of these industry-wide societal challenges? Once the proof of concept is done, it can be rolled out to the rest of the institutions in the marketplace. So that's required in order to solve one of these problems of productivity slowdown. Secondly, there isn't, as I mentioned, there's a significant cost of communicating between the scientists, the engineers, as well as the business managers. So if you take a simple example, following the pandemic, during the pandemic, people started buying a lot of things online. But when you bought a lot of things online, you also tend to return a lot of things online. So return a lot of things because you bought it online. Now, if you are a logistics firm in charge of distributing some of these products, The high-performance digital computers today can only do the computation overnight and an overnight run, basically, right? In order to work out which parcel should be sent to which address and which driver is going to do it, and so on and so forth. Now, if a lot of things are being returned during the day, you want to optimize, or you want to re-optimize, you want to calculate your routing almost on a continuous basis so that you reduce your cost of collecting the items the next day, and so on and so forth. But today, the computers are not able to do that. You probably need a quantum computer, right? So therefore, this process has got a lot of knock-on effects in terms of the inventory management, the financing, and so on and so forth. But understanding that, i.e., how do you get a shared language between the scientists, the engineers, and business managers to understand what kind of problems can be solved, what kind of information is required, how to prepare the data in quantum-ready format, needs to be further developed in order to reduce this cost of translation. And secondly, similar to digital computers, we need more common semantic and syntactic language for quantum computers, which is being developed, unified modeling language, a visual system, or modular workflow and prototype and test beds and roadmaps being developed, for example, in computational chemistry, but needs to be widened into other sectors in order to reduce that cost of translation, and therefore can be applied to different business problems. The third element is this idea of cryptographic costs, so to speak. So the principle here is we need a more secure system in order to prevent our encryption system today to be broken. And in order to do that, one way of thinking about it is to build a quantum internet, i.e., it'll be a complementary internet system to the current digital technology-based internet system, which will allow these quantum computers to talk to each other, i.e., just like what the digital computers, the internet did with digital computers, they connected all the digital computers, and we need a similar system for a quantum internet so that the quantum computers can talk to each other in a secure way, and it can allow for distributed computing, which would then generate, I suppose, security and economic growth. So, for example, British Telecoms, together with Toshiba, has got a pilot running in London using live cables between some of their clients, HSBC, Ernst & Young, and so on and so forth. And they've demonstrated that you can actually generate, I suppose, more secure keys using some of these quantum mechanical principles. They call it QKD, quantum key distribution, in order to encrypt data and transmit across fiber cables, and demonstrate that it is more secure, because as soon as somebody intervenes to read it, you know that somebody has intervened because of some of these quantum mechanical principles, and hence it's more secure. And what they're trying to do is to say, right, how do we then build on the back of this technology? How can we roll it out to the rest of the country, and to have a network orchestration and scheduling system to enable people or organizations to access and use some of this technology? So here's an example of where the business model innovation comes in, because in principle, if you have an encryption system based on some of these quantum mechanical principles, and you have a quantum computer, it's possible to do what is called blind computation, i.e., you can send a problem into a quantum computer, and the quantum computer can do the computation without the computer actually knowing what the precise computation that is being done. So today, if you take a firm like JP Morgan will never send any of its proprietary information to, let's say, Amazon or any of the data computational service providers and cloud service providers, because it's too risky. But in the future, it's possible to send a computation out to a third party to do a computation if the computer doesn't precisely know what the computation is, because your proprietary information is not being given away. An example of an application of this would be, imagine in a world where we have a distributed architecture for manufacturing, i.e. there's many factories using different, let's say, 3D printers. And each of these 3D printers has got a machine learning and AI algorithm that is improving the way in which it prints and manufactures certain type of products. Now, the learning from that can potentially be transferred across to another factory without the proprietary information of that process being transferred across, so to speak. In principle, it's possible to do that now, which means that in the future, there could be better optimization of network of factories and sharing capacity and localized production, which may even play into some of these climate change initiatives and such like. So that is an example of where a quantum-based internet could be very helpful in order to drive new business models and potential economic growth. Now, we've done a reasonable amount of work talking to some of the users and suppliers of this technology in the marketplace. And some of the lessons we learned is the UK in particular are leaders in science and engineering and quantum technology. We've been investing quite heavily in this sector for a long time. We've got lots of universities that are leaders in many of these technologies. And in some quantum technologies, for example, trapped ions and photonics, the UK has got a very large photonic sector. So we are well placed, I suppose, as a country in order to leverage this technology. In terms of Innovate UK funding, we've seen, which has been very effective. Over 150 businesses have been, business-led projects have been funded, over 1 billion private and public sector funding, extremely knowledgeable workforce. Over 200 PhDs have been supervised in this area, maths, physics, computer science, engineering. Funding from VCs is quite healthy, over 435 million, and as a vibrant startup community, i.e. over 40 startups just in the UK. Now, in order to really drive this, and we've written a white paper on the back of this, we need, as I mentioned earlier, a proof of concept, i.e. tackling a grand challenge problem in order to demonstrate the viability of some of these quantum computers. Enable system integrators, i.e. currently we, especially in the UK, do not have a large systems integrator like the IBMs of this world or the Microsoft of this world. How do we enable systems integrators to help bring the technology, the different components of the technology and the business applications together? Accessibility of IP is a major problem because some of these IPs are sitting across universities, and there are all kinds of issues around commercial and national scale-up of these technologies. And a lot of EPSRC funding and Innovate UK funding doesn't allow for the scale-up of the technology, so to speak. So we kind of cut off the funding at a relatively early TRL level. So therefore, when we look at manufacturing capacity, it's rather limited. And quantum business literacy, i.e. a lot of the initiatives are still very much focused on the science and the engineering, but very, very little on the business community. How do you get the business community, the senior executives, to understand the benefits of this technology, particularly given its complexity, and therefore drive some of these scale-up issues? So in the UK in particular, the UK government, because we do not have a systems integrator, i.e. large systems integrator like the IBMs, the Microsofts, the Amazons of this world, we have set up what is called the National Quantum Computing Center. Over 100 odd million have been put into this center just outside Oxford in Harwell. And about 6 or 7 months ago, they funded 7 testbeds, i.e. so these are testbeds that are physically having their quantum computers built in the NQCC Center, the National Quantum Computing Center. 3 of them are US firms and the rest are UK firms. And they are all based on different underlying quantum computing technology. So they're not all on the similar technology. So some are based on superconducting technology, some are based on photonics, and so on and so forth. And the idea is to benchmark these technologies in order to help these firms to scale up and to build an ecosystem around them. And also under the national program, there has been 5 hubs launched, EPSRC-funded hubs. This is the 3rd round of 5-year funding. So one of the ones that I'm involved in is the quantum computing hub that is led out of Oxford, and there are another 4 of them, totally 5 of them, looking at sensing, imaging, and timing, position navigation, and timing, as well as looking at quantum networks, and one on biomedical applications, so to speak. So the biomedical application one is led by UCL and at Cambridge. So the whole idea of some of these initiatives is not only to understand the prototyping, i.e. to build prototypes to demonstrate the proof of concept, but increasingly issues around how do you think about ecosystem and the business issues, the economic issues is coming to fore. And the idea is to build the ecosystem as the technology gets more mature in order to be able to scale up and therefore contribute to economic growth and productivity. So therefore, there's a lot of work, I suppose, to be done over the next 5, 10, 15 years or so. So it's unfolding. So just to summarize, there's motivation and potential for quantum technologies, a significant promise from quantum computing, significant public and private sector investment in the space. Business model innovation is very important to enable economic productivity, particularly the potential drag on productivity and the need to prepare for early for some of the challenges ahead. And finally, some of the initiatives for business and economic ecosystem development is very, very important and is becoming more important. How do you align incentive between the users and suppliers, and particularly building skills and business leadership, i.e., not just the technical skills, but how do you enable business managers and senior leadership to understand the implications for the core processes, the value creation, the business model development, and so on and so forth. Only then we'll really get the benefits of this technology, so to speak. So therefore, there's a number of programs of work we hope to be able to lead over the next few years. Thank you very much for that.
It's rare you get a talk when you feel you're really in the presence of an expert. I definitely felt that. There's so much to take from that.
Thank you.
It's going to be difficult for us to see, but I'm hoping we can see if there are any questions. Perhaps
I can see it here.
Oh, lovely.
Joined online for that reason.
Thank you, Soma. Thank you. Does anybody in the room want to ask a question?
I have a question.
Yeah.
Let's see if anybody's got a hand. So I found it a very fascinating talk. Thank you.
Thank you.
And you didn't use the dead cat example.
Oh, the dead cat. The floating of cat.
Yeah,
But my question is around, so when I go around talking to different sectors, of Met Office, defence, they seem to have a hesitation in investing in quantum.
Yeah.
And want that research to be funded by public sector or else somewhere else.
Yes. Yes.
And that's what I see you're showing with the scaling.
Yes.
So there's an assumption in your talk that everything can be scaled and the technology is ready. Whereas what you're hearing from the sector is something different. And I was wondering what your view is, where we're really at.
Yeah. No, the technology is certainly not ready, and there are different levels of readiness. So if you look at the application of quantum in the sensing and imaging, they're probably relatively more ready. When it comes to communication, there are some pilots being done in London and so on and so forth. So there is proof of concept, so to speak. Computing is the one that is least ready. But if we then look at the potential impact, it is completely the other way around. i.e., computing is the one that has potentially the largest impact. And all the VC funds are more interested in investing in the computing technology because that's where they think they're going to make the biggest returns, right? And you're absolutely right, Seema, in the sense that this is where I think the UK government, or not just the UK government, anywhere else as well, but apart from China, China is very different because they run it quite centrally. There is a tendency for other economies to think, well, you know what, the government should fund the early stage development and then the market should pick it up. And the market is probably unwilling to pick it up because people like DT are going to the government and say, well, it is actually a national infrastructure to some extent, so therefore it should be funded by government. And then maybe a conversation in government to say, oh no, actually the benefits is for the private sector, so therefore the private sector has to fund it. Right? So there's a little bit of a chicken and egg, and therefore where should we put our funds? And hence in our white paper we said, the government should actually fund the proof of concept, and the proof of concept should be on a big problem, so to speak, right? Where no individual firm will want to fund it, but it's an interest of everybody to see the value of that technology. Once the proof of concept is done, then you can open it up and people will come in to invest. And that bit is now being thought through as part of the quantum missions to say, how do we formulate such a program in order to show the proof of concept, and then hopefully it will scale up. But you're absolutely right. The technology is definitely not ready for deployment yet, but potentially very significant impact in the future.
People online?
Yeah, there's no questions on that.
Yeah.
Yes, we've got one question from Zamrat.
Hi, guys. I cannot turn on my camera, so apologize.
Zamrat, do you have a question? Do you want to?
Yeah. Can you hear me?
How do I do this?
Can you hear me, guys?
Zamrat, do you have a question?
Yeah, I do. Can you hear me?
Not hearing.
No, let me just try to.
Or we,
Yeah, try to,
No, we can't hear you. If you put it in the chat, maybe one of us can
yeah,
read
try
it.
now.
yeah, no, no.
Can I try now?
Can
The
you hear me
question?
now? Can you hear me now? Hello?
No.
I
Can
think,
you- no?
Summer, could you type the question in the chat, please? And then we'll read it out.
Maybe I could just answer the question on it. So I'm going to just focus on the organisation aspect.
Yes,
Yes. You refer to sort of barriers, and one of the barriers I was intrigued by is the cognitive drag.
Yes.
So the ability almost that business managers and won't understand this stuff and never really develop. I was intrigued by it because when we talk about AI,
Yes.
there's always this sense that there is a cognitive drag there because the technology is so difficult to understand, it's not understanding, and that's the point I'm going to say. So we black box it.
Yes.
So could you see that as an equivalent, and therefore do you see that as a potential inhibitor?
Yes.
So it's sort of how we might sort of overcome that.
Yes.
Cognitive drag. We start to black box.
I think so. I think there are some similarities and differences. I think the thing with AI is, I think we generally get the notion behind digital technologies in particular. And AI then is a advanced version of computation using digital technologies, right? So we may not necessarily understand the mathematics that behind it in order to do the computation, but in principle, it's just a complex algorithm.
Yeah.
Right, compared to any other type of algorithm, and that's what makes it black box, i.e. you don't understand the black box.
So that cognitive sense is easier because we can black box that fairly.
Exactly. Now, I think with quantum, it is the part of the problem is even the translation between the physicists and the engineers is already difficult. Yeah. Because what happens is the engineers will typically ask, how does that work? And the physicists will say, don't worry about how it works. Just trust me, it works.
Just scaling.
Yes,
that's their job.
Right, because the mathematics works and the empirics works, and so trust me, don't worry, right? So now the engineers are having to talk to the business managers, right? So the business managers are talking to the engineers and saying, but this sounds good, right? The scientist said to me, don't worry, just do it. Just invest in it, right?
A leap of faith.
A leap of faith, basically. And I think it's because the community still doesn't understand the underlying cause and effect of these quantum mechanical principles. And the philosophers are very involved in this as well, right? To say, what is this all about? What's the distinction between a subject and object? In science, we want to separate the subject and object. Right? Not in this, right?
They're two settings.
Exactly. In quantum mechanics, it is blurred. What a subject and object is. So scientists are very, very comfortable in a world where everything is objective out there and you can test it and so on and so forth. In quantum mechanics, this idea of what a subject is and object is becomes blurred.
Yeah.
And hence it's very difficult to communicate. And I think a way in which we can make people comfortable, right? You almost need to make yourself comfortable. And then, therefore, the translation between the scientists, and we hear this when we talk to some of our colleagues who are in the startup organizations. Oh, it's so difficult, even within the startup, for the scientists to talk to the engineers, right? And then now the engineers need to talk to them, and that's where it's different, I think.
And I was thinking, we've got the black box works for where we are with AI, digital technologies.
Yeah.
What would be the equivalent to try and get that sort of sense of a leap of faith? Is it a black box? Is it a blurred box? Is it a box?
I think you're right in the sense that, and this is where some of these tools and so on and so forth would become helpful to say, let us show you how it works. Very, very simple, diagrammatic, and that's what happened even in digital computers. So when digital computers first came on board, the thing is, when we never studied the evolution of digital computers as it unfolded, right? We are doing all the studies retrospectively.
Yes.
Right? So one of my reasons to get into this area is to say, why don't we study this as it unfolds? Because only then we can understand all of the failures. Right? And in digital computers, I presume the same thing happened when in the early stages, people thought of this as a little bit of a magic, right? How can you do this?
Right.
Over time, managers became comfortable, and therefore you take it for granted. Nobody's asking you how those transistors are working today. They got billions of them, in little square boxes. Please.
Yes, I have a question about the three competing systems that are out there at the moment.
Yes.
And whether you think that because there's ion trap, microwave and entanglement, I'm sort of thinking is
Yeah.
kind of the third
Yeah.
possibility, because
Yeah.
that one's on a slightly different set of physics, doesn't it?
Yeah.
So which of those do you think is, given that we always have this competitive race between different systems,
Yes.
which do you think is the
So from an engineering perspective, the problem is there's a trade-off. In the sense that there are two things that are important here. One is the fidelity of the
Yeah.
system, right? How
Yes.
long can you hold
that
instant particles in a particular position? And the second is the speed at which the computation can be done.
yes,
And there's a trade-off between the two in all of these different technologies. Right? So the ones where the fidelity is long, I've been talking about fidelity, we're talking about microseconds.
yes,
Right?
Yeah.
The ones where the fidelity is longer are the ones where the computation time is which way around is it? You've got stability, but then it's slow.
the air is creeping in.
Yes, and the errors are creeping in, right? Well, because the systems are all probabilistic, so to speak.
Yes,
So you're trading off all of these different requirements, and that's why you've got multiple technologies. Basically, this is better in this sense, that's better in that sense, but how do I make that better in all senses? And that's where the engineers are playing around with it. And it's very difficult to say which one is going to be the dominant design.
it is too early, isn't it?
Yes.
I keep reading about the differences between different systems,
Yes.
and in particular,
Yes.
sort of focus on photonics,
Yeah.
because you can take a synthetic diamond perhaps,
Yes.
and then you can kind of sequence
Yes.
superposition far more effectively to allow that
Correct.
computation to
Yeah.
take place.
Yeah, yeah.
Without the noise, so
Yes.
much noise.
Yes, and all of them have noise because it's quantum mechanical.
Yeah.
And therefore there is a level of error in the system. And so one of the companies in Cambridge, Riverlane,
Yeah.
is building a error correction system. So the layer that corrects the errors regardless of the underlying technology.
Because, as you say, you can't take that out, can't you? And it's almost, it's that built-in thing is if you're going to have superposition,
Yeah.
then you are going to get all sorts of different error states at times, aren't you?
Yeah, I think, and this is where the physicists have come in. I think in principle, it's possible to have a system that is error-free.
Yeah, that's the perfectionist.
That's the perfection.
Yes,
It's probably unlikely to happen in the short term.
yeah,
So there will be a noisy version of the system today that may be still useful before we get to this error-free system sometime down the line.
Yeah.
And the question then becomes if a firm like Riverlane is able to build a robust enough error correction system, they become the bottleneck
yes,
for the industry to say everybody who wants to build something will need to have this layer in place and so on and so forth.
that's the other question I have about this.
Yeah.
Is kind of those sort of almost tipping point technologies.
Yeah.
So I keep reading about the different kind of the modularity that needs to come in particular, building interfaces between the different components of, for example, a supercomputer.
Yes.
So that you can build them in a way that you can then develop modular systems out of them,
Yes.
but also then in terms of how do you reduce the error correction problem in your design complexity.
Yeah, exactly.
So that seems to be another place where there needs to be a bridging technology of some kind come along that enables all of the different systems
Yes.
to kind of reach that level of system integrity.
Yes. And that's why the National Quantum Computing Center has picked 7 test beds.
Yeah.
All of them are different technologies,
Yes,
underlying technologies. So then they're benchmarking the technologies with the view of then benchmarking against use cases, right? To say, now it's possible. In principle,
Yeah.
it's possible that maybe for a financial services industry, superconducting is better,
Yeah.
but for pharmaceuticals, something else is better. It's possible.
Right.
that's
And the issue is the following. So this is the other thing that I learned more recently. If you are a systems integrator and
Yeah.
you are building a contract with a
Yeah.
supplier, right? One of the things apparently a system integrator always has is a get out clause. What happens if the company that you're contracted with fails?
Right.
Then you have to have an alternative provider. Now, the problem with quantum computing is you've got 7 different technologies.
yes,
The alternative is not clear, and therefore I will not want to invest in,
That's the other thing, is that the investment market isn't there quite, is it? Like it's
Right, right.
there's a public sector investment in
yes,
it.
yeah.
The investment model is not clear, is it?
Exactly. So this is where all of these issues are kicking in.
Yes,
And how you de-risk the system.
yes,
In such a way that you kind of get a better picture of which will be the
Yes.
dominant design.
Except for right now, you're saying government, all the private sector firms are saying, because we're so much of TRL one,
Yes,
that the investment needs to come from
yes,
as national infrastructure.
yes. In some sense, it needs to, because without that public sector investment, the de-risking wouldn't happen.
yes,
And everyone will say, well, I'll just wait, right? I will invest
Of course.
enough just to keep
Yeah,
pace
yeah,
of the
yeah,
knowledge.
yeah,
I'm not going to put any money in
yeah.
because I may be betting on the wrong one.
Yeah.
Right? Everybody's just waiting and, whereas I think, this is where I don't know enough about China. In China, the programs run more centrally. And therefore, in some sense, there's an advantage because there's, right? It's kind of interesting, right?
Yeah.
Very, very early technologies, you almost need that
Yeah.
central.
Yes.
To work out what's worked and what hasn't worked and what we can push.
Yes,
Yeah.
yes, and that's where we are with this technology. Everything is like, okay, we know the science, we kind of know the engineering.
Yeah.
But we want to now put it all together to scale it,
yes,
and nobody's willing to invest. Everybody's like holding off. So to speak.
Yes.
That's why your use case is so important. Your proof of concept is so important.
Yes, the proof of concept has to be demonstrated only then, and the proof of concept has to be demonstrated not on the benefit of any one individual firm.
yeah,
There has to be a problem,
it does have to be, as you were saying, a major challenge,
a grand challenge, right? That nobody will invest in.
Yeah, and that's what I've seen in the business.
Yes, yes, exactly.
Yeah, the two questions. Yeah.
Maybe we should wrap it up.
On slide 11, I think can you explain the qubit formula in the context of comparing binary and quantum modalities? Well, it looks like implies that infinite combinations are not possible. Okay, which one is slide 11? Slide, right. I think
It was your 0 to 1. What's that one?
it's the cat one. Oh, the zero.
The 0 to 1 and going anywhere in between.
Okay, I see.
I'm guessing.
Slide 11.
No, don't just-
Okay. Oh yeah.
Yeah, this
Oh yeah.
one.
Oh yeah. Okay.
Yeah, yeah.
And,
Oh, okay.
let me see what's the question, if I could.
If it's infinite number between 0 and 1.
Oh, okay. So the idea, the way to think about it is in a digital computer, what is happening is we are switching electricity on and off.
Mhm.
And the microprocessor is enabling that process to happen faster and faster with all the transistors. We're packing more and more transistors, right? So effectively what we're doing is we're encoding information in that 0 and 1 space. In a particle that is quantum mechanical, it's not. So the way to think about it is you've got this block sphere, if you think about it, right? There's a 0 and 1 at the top, and it can be in anything between the 0 and 1 in terms of probabilities. i.e., there's a probability that it could be 20% 0 and 80% 1, or it could be the other way around. Or in the other complication here is it can also be in a negative state, so to speak. The probabilities can be in -1 state, so to speak, i.e. in the sense that we are using complex numbers. So therefore, there's a block sphere that is encapsulating the possibility that it can be in the 0 and 1 space with some probability, but it can also be in the complex number region, right? And when you take a reading, it will flip to 0 and 1 on the basis of that probability, right? So going back to my cat example, if there are two cats there, there's a probability the cat would be in one of these at a 50%. So therefore, you can set up, let's say, the calculation of the particles in such a way that there's a 50% chance that it'll be in 0 and 1, and then you're passing it through these two boxes. If the cat is there, it will flip to 1 or 0, but if it flips, you know that the other would be the opposite.
Yes, and then that gives you a huge range of probability, doesn't it?
Yes. To play around with.
Yes.
Yeah, exactly, right? So now imagine you've got a very, very complex problem. The same issue is arising because you've got a computation to come up with a solution. And when you entangle it, you're doing effectively the same thing in order to reduce the number of steps to get to the computation. So in that sense, that's how that, the block sphere of the qubit works, so to speak. You can physically, I suppose, from a physics perspective, you can set it up in such a way that there's some probability that it'll flip to 0 or 1, and then you take a measurement, and then you see what happens, and then you do the computation accordingly.
And that's where it's genius, isn't it? That's the.
It's amazing. I mean, it's mind-boggling. And the other thing, one more other thing I wanted to emphasize is in a digital system, when you flip something from 0 to 1 or 1 to 0, you don't know the history. You don't know whether it has gone from 0 to 1 or was it always 1. Right? In a quantum mechanical system, you can trace the history back so that you can know it was in this state, you flipped it to that state, you can flip it back, see.
Yeah, and then you can work out prediction from that too. can't
Right,
you?
exactly.
From that,
Yeah.
yes.
So it's a combination of these factors that allows you to do faster computation, if that makes sense.
I think we have to call it all because we're at quarter past. I think that was outstanding, and I think we all thoroughly enjoyed that.
Yes,
Thank you very much, Roger. Thank you. Thank you so much.
Brilliant, absolutely fantastic. Would you like a cup of tea? Would you like to chill for a second? Come on, let's get you out of this very
Lovely cup of tea would be perfect. Yeah, excellent. Thank you.